We got that going. Let's take a look at number 13. So in this problem, they give us the ends of the diameter. You probably saw some similar problems on iExcel when I assigned that over the weekend. So if you need more practice on that, I suggest maybe taking a look at iExcel again and practicing. Oops. So we have here a circle that has a diameter with ends at -17, -9. So I'm just going to do like a rough, let's say -17 is here, -9 is here. So there's 1 point, and -19, -9. So say that's -19, there's -9. So we have a circle that's right in here. That's our diameter. Oops. Right there. In order to write the equation of a circle, we need to know what the center is, and we need to know what the radius is. So if we know the diameter, then we can go ahead and find the radius by just cutting that in half. You should have finished up to number 14, numbers 1 through 14. So if this is the diameter, it's a measure of 2 units. From -17 to -19, that's a total measurement of 2. So that means that the radius has to be measured by 1 unit. So R is equal to 1. And then our center, we just can figure out it's right in the middle there. Between -17 and -19, we have -18. So that's going to be the point -18, -9. So we have the center and the radius, and now all we have to do is just plug that into our standard form. So our standard form is x minus h squared plus y minus k squared equal to r squared. And then we can plug in the center. Remember, when you plug it in, it turns opposite because you already have the 2 minuses here. So that's going to become x plus 18 squared plus y plus 9 squared. And we said r is equal to 1. The radius measures 1. So equals 1 squared, which is equal to 1. And that should be your equation there. Okay. Let me know if you have any questions, if you'd like me to clarify anything. And we'll take a look at number 8 next. So there's, erase that so it doesn't look as confusing. There's 13 and number 8. So they've already given us the center and the radius, which is nice. We don't have to try and figure it out. All we have to do is plug it in. So x minus h, if our h is -6, it's going to become x plus 6 squared plus y plus 15 squared. We just plug in -15, so it becomes positive. And the radius is √5, so that means our r is √5, but our r has to be squared. So when you plug it in and then you can simplify the equation, we get x plus 6 squared plus y plus 15 squared equals just 5, since the root and the square cancel each other out. Oops. And that's our equation. Any questions on that? Let me know. Are there any other problems that you'd like for me to review before we move on to ellipses? Number 14, okay. So 14 is similar to 13. They're both giving us the ends of a diameter. So again, I like to just sketch so I can see kind of what this is going to look like. We've got -3, 11. We'll just say that's 11 there. Just a rough sketch. And then we've got +3 and -13. Again, we'll just do a little rough sketch there, like that. So we have this circle. It's a bit of a bigger circle there. Something like that. Okay. And we need to figure out what is the measurement of this diameter, so that way we can figure out what the radius is. So in this case, because they're not lined up perfectly, like in this problem here, we could easily just calculate what the radius was because the diameter was just straight across. In this case, the diameter that they gave us, we have this distance here that we need to figure out what the measurement of that distance is, and then cut that in half so we can find the radius. So, sorry, I'm doing attendance as it goes. Need to update it real quick. Give me just 1 second. And okay. So like I was saying, we have to figure out what the distance of this line is. So we would have to use the distance formula, or we could also use Pythagorean's theorem. It's up to you. They're the same thing, actually. When you end up doing both, it's the same formula. Pythagorean's theorem is kind of easy for us to figure out because we can calculate what this distance is and what that distance would be. So you have that right triangle there. This total distance is going to be from 11 to -13, or the absolute value of -13. So it's going to total up to 24. Right, so that whole side of the triangle is 24. And then this shorter side over here is going from -3 to 3. So it's a total distance of 6. So we have 24 and 6 as the two legs of that right triangle. And then we just need to figure out what this distance is, because that's going to be our diameter. So it's just going to be 24 squared plus 6 squared equals the diameter squared, since the diameter is the hypotenuse in this case. And then we are going to just plug that into our calculators. And oops, what is that going to give us? 24 squared is 576 plus 36 equals d squared. and that's going to be d squared is equal to 612. And then we'll take the square root of that. And that's going to give us some decimal, but we'll just keep it simplified. It'll become 6 root 17. And that's because 612, if I take that, 612 is equal to 36 times 17. And 36 is a perfect square, right? 6 times 6 is 36. So that's why we're able to pull out the 6 in front, because the square root of 36 is 6, and that leaves us with 6 root 17. So now our radius is going to have to be half of that diameter, which will just be 3 root 17. So that's our radius, and then we just need to figure out what our center will be. Sorry, one more second for attendance. Should be the last time. Okay, sorry about that. So we need to find the center, and that is going to be what, oops. When we take this circle here, we know that it's going to fall right in between there. So if we kind of take this new right triangle there, we know that this is going to measure 3 root 17, and this height is going to be 11. So we need to figure out what this measurement is right here, right? So again, we're going to have to use Pythagorean's theorem. This will be 11 squared plus b squared is equal to 3 root 17 all squared. And so if we can figure out what that measurement is, then we can find that center point, okay? This problem, I won't really expect you to have to do all of these extra steps when it comes to the equation of the circle. So what I will do is I will write out the solutions to this. So if you're interested, you can follow along to it. But I don't want to spend too much time on this because I'm looking at the time. I want to make sure that we can get through ellipses. So I'm going to post the solution for the rest of this problem if you're curious about it. This is kind of like another challenge problem there. So don't worry too much about it if there's seems to be like too many steps there, but do try and check it out and see if you can follow the steps to it, especially if you followed this far so far. So I will post that, and what I want to do is move on to ellipses now, so we can kind of have enough time to go through that. Let me know if you have any other questions on this. We're definitely going to come back and review this as we kind of continue through all the different conic sections, but I want to make sure that we get started with ellipses now. So there's a new set of notes that has been posted on Schoology that says ellipse, and we are going to take a look at that next. And when we start out, we have a lot of vocab that we need to discuss and talk about. When it came to the circle, we only had basically 2, if not maybe 3, when we throw in the diameter, different terms that we had to discuss. So we had the center, and then we had the radius. And we knew that the measurement of whatever that radius is going to be the same measurement all the way around. So I can draw a line anywhere here, and it's going to measure the same thing. It's going to measure whatever the radius is. I can pick any point, and I know that distance will be the same. Well, when it comes to the ellipse, it's a bit of a different property that we can use to define the ellipse. So I'll read out the definition, but then I'm going to show you kind of a demonstration of what this means. So the ellipse is the locus of points, and if you haven't heard of the word locus, basically it just means the set of points in a plane, such that the sum of the distances from two fixed points, which we call the foci, is constant. So I'm going to show you this animation here. So what the definition is saying is that I can pick any point on the ellipse, and the measure, if you look at the measure of the blue line and the measure of the red line, when you add them up, it's going to be the same length all the way through. So if you look at it moving around, we see that the blue line maybe is getting longer at some point, but if the blue line is getting longer, then you can see that the red line should be getting shorter. That is because they're always going to equal a total length of 10. So when you add them up, it should equal 10. So if the blue line all of a sudden starts getting shorter, the red line should be getting longer, right? And it kind of like moves in that same pattern all the way around. The blue line gets longer, and so the red is getting shorter, and then the red gets longer, and the blue gets shorter. That's to maintain that equality, right? So if the blue line measures 9, the red line we know should measure 1. Blue line measures 5, red line should measure 5, because they should always have the same length. So that's the definition of an ellipse. We can take any 2 points. So the 2 points are the points that we see kind of inside of the ellipse, where the blue line starts and the red line starts. That's what we call the foci. In plural, we call it foci. Sorry, there's something going on outside. So the plural form is foci, and the singular form is focus. So each one of those points is what we call a focus. Together, it's the foci. So we have the foci points. Basically, we can pick any 2 points. If we were kind of in class, we probably would have done an activity where you would draw out 2 points, any 2 points. And if you have the measure, let's say your measure is 10, total of 10, then you can take that measurement. Let's say this would have to be 5 and 5. So we know this point exists on the ellipse, right? And then we would know that that's 5 and 5. So we know that point exists on the ellipse. And so you can keep drawing in points that measure, that continue to measure 10, and eventually you will get that elliptical shape. But it's all based on the foci. So maybe if your foci are closer together, your ellipse is going to be closer to what might look like a circle. If your foci are farther apart, then your ellipse might become more elongated, just kind of depending on the foci and depending on the measure that the lengths sum up to, right? But that's going to be the definition of an ellipse. It's the set of points such that the sum of the distances from those two foci is constant. So we've looked at foci, we've kind of defined that there. And then we're going to look at the major axis. So the major axis is the line that goes through the foci and is our longer side. So that's what we call the major axis. The minor axis is going to be the shorter side. So when you have the ellipse, you're going to have different measurements, right? Otherwise, it would be called a circle if it was the same measurement all the way through. But since we have different measurements, our way of defining which one is the shorter side, which one is the longer one, is with major axis and minor axis. And both of those major and minor axes go through the center. So you have that going through the center. And obviously then we have the center. That's going to be right in the middle. And then vertices. So the vertices is the plural form of vertex. And we can see in the picture, the vertex are the very furthest points that are on the major axis, so on the longer side. If I were to flip this ellipse this way, then these would be my vertices, because now those are on the longer side. And that would mean that this is my major axis, because now that's my longer side. So then our co-vertices, or singular covertex and covertex, those are on the shorter side. So in this case, those would be our two covertices because they're on the shorter side. Eccentricity is something that we're not going to spend too much of our focus on. It basically measures how circular or stretched out the ellipse will be. I was talking just now about how the distance between the foci is going to make a difference on how stretched out or how kind of circular it's going to be. So this is kind of the ratio that creates that. We're going to talk a little bit more about what A and C stand for and what it represents, but that's the formula there. We'll maybe do some examples where we find the eccentricity, but we won't really focus too much on that. Our main focus is going to be, just like with circles, writing the equation of the ellipse and then graphing ellipses as well. So here we're going to take a look at the standard form of an ellipse, or the equation. And if you remember from the general form, which was ax squared plus bxy plus cy squared plus dx x plus ey plus f. That was the general form. In order for it to be an ellipse, A and C had to be different. They had to be different coefficients, but the same sign. So they could be, for example, 4x squared and 9y squared, right? They just had to be different values. Otherwise, if they were the same, then it would be a circle. And they have to be same sign because otherwise it would become a hyperbola. So we're going off that, and we're going off the assumption here that A is greater than B. So that means A is the longer side. So in this case, what I want you to pay attention to here, this is a horizontal ellipse, and that is because we see it's longer on the horizontal side. And if you notice the equation here, it actually almost looks like the equation of a circle. We have x minus h squared plus y minus k squared. That's the same exact thing that we had with a circle. But now we have these two values down here. We have a squared and b squared. And a, remember, is greater than b, so a represents the longer side. And if you look at this kind of connection here, the longer side, whatever is on top of it is going to tell you the direction of the ellipse. So if we have a is the bigger value and x minus h is up top, that means the x, which is horizontal, is telling us it's going to be a horizontal ellipse. Now look over here. Remember, a is the bigger side right there. A is now underneath y minus k squared. So that means we have a vertical ellipse because it's going to be longer, right? A is longer and it's underneath y. So its y-axis is vertical, so that means we have a vertical ellipse. So that's telling us our major axis, right? The major axis is going to be the horizontal line in this case, and in this case, the vertical line. So actually, when it comes to ellipses, the order doesn't necessarily matter because it's addition, right? And they have to be the same sign. So I could technically write this as y minus k squared over a squared plus x minus h squared over b squared equal to 1. That's still the same thing as long as a is still the bigger side. So the bigger side should always be underneath whatever side our ellipse is going to be, right? If it's going to be horizontal, then it should be under the x. If it's vertical, it should be under the y. So we have all these different parts that we should be able to find. So the center is going to be the same as a circle. It's going to be HK. So this is our center. That's just HK, the same way the center of a circle is HK. And so this same part right here, H and K. When you plug it in, again, it's going to be opposite. The foci is H plus or minus C. So we're going to have to talk about C and where C comes from. But if we look at, this is one foci and that's the other foci. So the distance from the center to either one of the foci is going to be measured by lowercase c. Okay. we said that this one, in this case, it's a major axis. So that would mean that the distance from the center to this point right here, which is our vertex, is going to have to measure A. So we have the measurement of A, and then we have the measurement of C, and then we need B, and B is going to be from the center to the co-vertices. So that measures as B. And then obviously we have symmetry going on here. So this is going to measure the same thing. It'll be measured by B. And then same thing for A. And same thing for C. So we have all of those measurements all the way around. But the important part to know is from the center to the vertex is A. From the center to the co-vertex is B. And then from the center to the focus is C. Okay. Now, in the ellipse, it doesn't necessarily make a right triangle, which is why we're not using Pythagorean's theorem, but we're using something that looks very similar to Pythagorean's theorem, and that is C squared is equal to A squared minus B squared. So there's a difference there. Instead of A squared plus B squared, it's A squared minus B squared. So this equation here will be useful when it comes to finding all those different parts. This means that if we know what A and B is, we can solve for C, or maybe we know what C and A are, then we can solve for B. It gives us different options to be able to find all those different parts. And just really quickly going to the vertical side, all of this remains true. So from the center to the focus, that's going to measure C. From the center to the vertex, that is going to measure A. So different from the other side, right? They're switched, but that's because the whole ellipse is flipped. And then center to co-vertex, that is going to be our B. We're going to jump into examples so that hopefully these parts will make a little bit more sense once we do the examples and kind of see how it works that way. So in order to write the equation of the ellipse, we have our standard form, which is x minus h squared over a squared plus y minus k squared over b squared is equal to 1. So that's one difference from the circle. Instead of having the radius, because now we don't have a radius, we just have it equal to 1 on that side. So this would be a kind of depending on the size of A and B. It can be vertical or horizontal. In this case, we have a horizontal ellipse, right? The longer side is along the x-axis. So that means that our A value here should be that longer side. So if I look at the ellipse, what I want to do is find what is the total measure here, and then divide that in half. So that way I can figure out what the measure of my A is. So I'm going from -4 to +6. That means it's a total distance of 10. So half of that would have to be 5. So I know that my A is going to measure 5, and I get to plug that in here. And I know I have to make sure it's going underneath that X value because it is a horizontal ellipse. Then I can figure out what B is by finding the measurement from here to there, that total measure, and then cutting that in half. So this is going from 7 to 1, which gives us a total measure of 6. So then from the center to that co-vertex, we get a measurement of 3. That's half of that, okay? So now we know our A and our B. A is 5, B is 3. So I can plug in 3 here. And we're almost done with writing the equation. The next thing that we need to figure out is the center. So from the graph here, I can tell that this is my center point, which is going to be 1, 4. So I'm going to plug that in here. And there is my equation of the ellipse. X minus 1 squared divided by 5 squared. So that you can change that to 25. I can write it out here. Minus y squared divided by 25 plus y minus 4 squared divided by 9 is equal to 1. So to find the center, it's the point. We found it kind of in 2 ways. It's the point that's halfway through the major axis and also halfway through the minor axis, right? So we kind of found this point by cutting each of those in half. So then all I had to do was look at the matching coordinates. So this was 1, this was 4. So I knew that the point was 1, 4. Okay, any other questions, let me know. We are gonna jump to the next problem. So this one is now a vertical ellipse. So with the vertical ellipse, we want to make sure that our longer side is underneath the y value. So sometimes what I like to do is just kind of write x minus h squared plus y minus k squared equal to 1. And then I'm going to figure out where the bottom parts are going to go. So our longer side here is going from -6 to 0. So that means it's a total measure of 6. And half of that is 3. So I know that my A will have to equal 3. And that's my longer side. So that's going to go on that side underneath the y. Okay. Because the longest side always has to go underneath whatever, whether it's x or y, depending on if it's vertical or horizontal. Okay. And then from here, let's do a different color. The total measure from co-vertex to co-vertex is going from -2 to 2. So that measures 4 total. And then if we cut that in half, that gives us b is equal to 2. So I'm going to go ahead and put 2 squared underneath x. Now we need to find the center. So again, we've kind of found the center already. It's that point where we see those two kind of intersecting there. So the point, let me kind of clean this up so we can see better. This point is at 0, -3. So I will plug that in here and plug that in here. That's going to make this a +3. So our equation, when I simplify this, will be x squared over 4 plus y plus 3 squared over 9 equal to 1. Okay. All right, let's do this next one, part C. So the first thing you want to think to yourself is this a vertical or is this a horizontal ellipse? And I see that it's kind of laying on its side, so this is a horizontal ellipse. So I know that my biggest value, my biggest side, is going to have to go underneath x. So when I write this out, x minus h squared plus y minus k squared equal to 1. Whatever that measures, it's going to go down here. I'm going to square that down underneath the x value. So let's go ahead and figure out what that is. This total distance is going from 0 to -8, so that's a total distance of 8, and half of that would be 4. So I know a is equal to 4. I can go ahead and put that right underneath x. And now we'll do the other side. So I'm going to check this total distance here. That's going from 1 to -5. So that's going to be a total distance of 6 all the way through. And then I can cut that in half, so then that gives me b equal to 3. And that's going to go underneath y, and we square that. Our center, come right here. That center point is going to be at -4, -2. Just kind of eyeballing it here, we can see that's -4, that's -2. So there's our center. So then when we plug it in, it'll become +4 and then +2. So simplifying this, we get x plus 4 squared over 16 plus y plus 2 squared over 9 is equal to 1. All right. Do you have any questions on that part? Writing the equation. So we can actually see for the equation, it doesn't take too much, right? We just need to know where the center is, and then we need to know how far to the right and how far up, or how far in each direction to go. And that gives us the ellipse. That's the bare minimum that we need. However, we know that in order to draw a full ellipse, we need to know what those foci are, because they're the definition of an ellipse is based off of those two foci. So they are important. We do need to know the foci. In most cases, we need to have that information. But you can't just see that from the equation, because when you have the written out standard form, all you can tell is the center and the measure of the major and the minor axes. Okay. So that's going to be enough for us to be able to graph if it's already in standard form. So when I look at this equation here, x squared divided by 9 plus y squared divided by 16 equal to 1. This is actually telling me a lot about the ellipse. So first of all, I can see that my center is at 0, 0 because I'm not adding or subtracting anything to the x or the y. So technically this could be written like that. So I know my center is 0, 0. I also can figure out if it's a vertical or a horizontal ellipse because I can see the bigger side is underneath y. So I know that it's going to be a vertical ellipse. And what we want to do is we want to square root those values so we can figure out that measurement. So the square root of 9 is 3. So technically 9 is the same thing as 3 squared. And 16 is the same thing as 4 squared. So we can actually see the measure of A and B once we just square root that. So we know it's going to be 3 and 4. And 4 is going to be the longer side. So we have our center here. 4 is underneath y, so we're going to go 1, 2, 3, 4. There's a vertex. 1, 2, 3, 4. There's another vertex. And then 3 is going to be my shorter side. Right there. And then I can just connect my dots. And there's my ellipse. Please let me know if you have any questions. This next problem, we're going to start to combine everything that we've done. So we're kind of not completing the square just yet. We're going to do that in part C. But we're going to be kind of, we'll see. We'll look at this problem. So our standard form has a 1 on that side. So that means this is not in standard form. We need to get it into standard form. It actually looks like the general form, sort of. If we look at part C, actually not part C. Oh, I'm jumping to these. All right, these down here, these are in full general form, which we're going to have to complete the square in order to solve that. We're going to get to that on Friday. But if we look at B and C, they're already completed squares, but they're not in the standard form. So we want to get it into the standard form. We want to get this 36 to be a 1. So in order to do that, all we need to do is divide by 36, because anything divided by itself is going to equal 1. And I'm going to do that to every single term, because we have to maintain that equality, right? So if we are dividing by 36 on one side, we have to do the same thing to the other side. And since we have 2 terms on the other side, we have to do it to both of those terms. So this will now become 4x squared divided by 36, which we can simplify. 4 over 36, that's the same thing as 1/9. So this is actually just x squared over 9 plus this fraction here, 9 over 36, is equal to 1/4. So this becomes y squared over 4. And on the other side, we have the 1. So now this is in standard form. Yay. Now it's the same thing as what we did in part A. And actually you can see it's very similar except for we have the 4 instead of 16. So that means that now this is our bigger side. So now we have a ellipse that is horizontal, and we also have a center of 0, 0. So we can draw in the center. 9 is the same thing as 3 squared. So I know that that's going to measure 3 in both directions. I put it along the x-axis because it's underneath x. And then underneath y, we have 4, which is 2 squared. So that means I'm going to go up 2 and down 2. And there is my horizontal ellipse. All right. That's going to be the end of class for today. I know this was a lot that I had to throw at you today, so I apologize for that. We're going to do more practice and things on Friday, and hopefully get into writing from general form to standard form on Friday as well. All right. Have a great day, everyone, and please stop by tutoring if you have any questions or want to review this. I did post a sign up for one-on-one meetings. If you want to talk about your grade, you can sign up for that. I haven't checked. There may or may not be extra spots left, but if there's not, just give me an email and we can try and figure out what time works. All right. So that is it for today, folks. I will see you on Friday. Goodbye.